Good afternoon, everyone. My name is Ed Holden. I'm with HPE, and we're here to talk about autonomous driving solutions built upon Cloudline hardware, built on open hardware principles. Do it manually. As everyone knows, autonomous driving is starting to become reality. We have lots of test beds happening these days with various auto manufacturers. And while it's great for the consumers and the people that are driving or not driving these cars, it's going to cause challenges to the manufacturers and the data center operators when we're talking about the amount of data that's required and the latency and the throughput that a successful autonomous driving solution is going to realize. So we're going to look at a couple different examples of how a company can build an autonomous driving solution built on open principles, both via hardware and software, and see kind of how this technology is moving forward at a pretty accelerated pace. Right now, if we're going to do this with today's technology, we have some limitations, as in the current cellular technology is at 4G, and that is going to create a little bit of bottleneck as far as the information that goes from the car to the data center and then back to the car. So currently, how this looks is your vehicle is driving along down the road. It takes about 500 miles between where your car is and the nearest kind of cloud data center where this might be hosted. So think of a Microsoft Azure data center, Amazon AWS. So in the time that a car takes to drive from that data to leave the car, hit data center, and then come back, you're going to have about 80 milliseconds of latency. In that time, your car will travel about 4 feet. Now that might not seem like a lot, but when you're driving 80 miles an hour, a lot of things can happen in 4 feet. So it's not ideal for a fully autonomous driving solution. So what we're looking at is in the next generation, when 5G is rolled out, you'll see some instances where companies are building micro data centers closer to cell towers. That's in order to, the data doesn't have to go as far. So the cars driving along, be data centers under and or near cell towers. It's going to increase or lower the latency as well. So the 5G technology itself is better at distributing the load, but also a lot better latency. So now what you're doing is average of about 5 miles for this data to travel from the car to a micro data center, round trip back to the car. Now you're looking at 5 milliseconds latency. In that time it takes for that data to travel round trip, your car now has only moved 4 inches. Now we're talking a fully autonomous driving solution, all the telemetry moving from the car to the data center and back. In the future, we'll have auto-to-auto transmission, so not all the data needs to go data center. Sometimes the cars will talk to each other on the roads, and 5G enables that as well. That'll help, with traffic jams, when the cars talk to each other. Again, that's going to rely on 5G to get the type of speed and latency for the auto-to-auto communications. This is also it's not just for autonomous driving, any kind of big data streaming application, whether it's IoT sensors, drones, construction, manufacturing sites. This is the same type of data path that you're going to realize, whether it's autonomous driving or some kind of other big data analytics streaming service. So this is an example of what the hardware would look like. In this case, a proof of concept we did for an auto manufacturer for their autonomous driving solution. So obviously you're going to have telemetry data coming from the car. That's going to be obviously the speed, possibly video, LiDAR, radar, multiple streams of telemetry coming from the car. And that'll go to the data center, whether it's a cloud-based data center or a micro data center near a cell tower. So that's going to come in, and you're going to have IoT events coming into a server. So in this case, we'll be running either an edge line, if it's maybe a hardened, at the cell tower, or if it's in a micro data center, you can have a Cloudline 2600, which is our open hardware standard version. of a 2U2P server. The events will come into that server, and then we need to process data. So we have the real-time analytics need fast NVMe-based compute. So we have a Cloudline 3100 with 20 NVMe drives, which will do the real-time analytics. We'll move that offline to a large form factor drive-based system. So again, in this case, we use the 3100 with 12 large form factor drives for analysis of the data at rest. And then that'll move to your data lake. So after the real-time analytics is done, you can move the data, you can format it to the S3 format if you want, and store it either locally at your object storage box, or offload that to your object storage S3 or Microsoft Azure Cloud. A little bit more on what this looks like with the software on top of it. So we have, again, the IoT events coming in to a traditional workload server, a 2U2P or a 1U2P. We have Kafka then running on the high-speed I/O server. So this is going to be, again, the Cloudline 3100 with 20 NVMe drives. That is where the real-time analytics is going to happen. All the messaging comes in with the streaming data, and we're able to process on this server 1.3 million messages a second with this NVMe server. To put that in perspective, spinning disk or non-NVMe would probably cap out at about 700 to 800,000 messages a second. So in this case, NVMe is really important to get the amount of data processed in real time. We'll then move that to a Kafka S3 connector, where we're going to convert the data and serialize it, convert it into S3 format. We're doing that again on a Cloudline 3100, but with spinning media. So this one will have 12 large form factor drives. Think like a Hadoop type server, something with bigger hard drives, but you don't need the performance for this application. For our proof of concept, we were doing about 12 billion messages in 24 hours processed and converting into S3 format. And then you're going to go offline. In this case, for the proof of concept, the customer wanted to store the data via a scality ring. So they have object storage servers in a scality ring, which then they can keep for further processing and analytics, or then move off-site to their cloud data center via S3 or Azure storage. So as far as the software goes, primarily, and this isn't just for autonomous driving, this is any kind of big data analytics streaming application, we're primarily focusing on the SMAC stack plus Flink, so that's Apache Spark, Mesos, Akka, Cassandra, and Kafka. We're seeing a lot of the users now wanting to use Flink for their open source stream processing framework, again for distributed, really high performance streaming applications. So that is becoming more popular as an application for this type of workload. Again, a little bit more of a diagram on how the hardware works. Again, the events come in from the telemetry data from the cars. You have a Kafka cluster up front, which does the real-time analytics, and then the big data at rest analytics. We'll use Flink for the router, and then that gets offloaded to your data lake, in this case, using a scality ring. This could also be done via a Ceph, Swift, any kind of object storage server and application. As far as the hardware we're talking about, in the HPE Cloudline portfolio, again, we are focusing on hardware built on open principles. So we have the HPE 2600 and the 2800. Those are more open versions of the DL360 and the DL380. No ILO, no smart array. We use off-the-shelf commodities, standard firmware, AMI BIOS. So again, this is for hyperscale customers that maybe have their own management stack. They don't really maybe value some of the things that they get out of ILO. So these are made to build at scale, very cost competitive for a larger type customer that is used to servicing their own systems and has the ability to do their own scripting, their own management, and then they're looking for someone to run Redfish or I don't think we want to talk about IPMI anymore, but any kind of open hardware standard for management and monitoring. The compute servers, as we said, a mixture of NVMe-based and spinning disks. So again, this is a 1U with 20 NVMe drives for the real-time analytics, or for the data at rest, the Hadoop style, just a same product, but with 12 large form factor hard drives. We also have dense compute. This is more geared for HPC type applications, but we have the 4100 product, which is a 1U with 2 individual dual Xeon compute nodes, or single socket AMD-based EPYC processor. For the data lakes, we have a couple different models. We have a 4U with up to 80 hard drives. You can have 1 or 2 compute nodes in that. Or for very large data lakes and or something like storage as a service, we have our Cloudline 5800, which is a 4U box with 100 hard drives in it. That's about all the time I have. Again, if you have questions, you can buy me a coffee right over there. We'll be also in booth C6. We have the 5800 and the 3100, the NVMe server over there, as well as some demonstrations on the CL4150 and Mellanox booth, and the CL2800 is in our booth at C6 as well. Thank you very much.